Okay. Well, let's see. So let me get over to here. And this is not it. Let's go to here. I put on this afternoon another assignment, which I hope you can see, from determinants, due next Tuesday. And here they are. And then this is the updated text down here. So can everybody access that assignment from Canvas and the updated text? Okay. All right. Well, then that should be fine. So let me go and let's take a look at some of these questions. I just thought we could read through them and make sure that we're on the same page as to what they mean. First of all, I think there were a couple of videos for this chapter. I don't think I made video for the last section, but I think there were videos for the first couple of sections. Is that correct?
I believe that's correct. I haven't
Okay.
watched them all yet.
Okay. All right. Well, here we go with this one, and make it bigger. All right. So let's see what we got. So we should be looking at 8.3 here. And these are extensively rewritten. They were not in good shape when I looked at them. Unfortunately, I think the quality of the book is, well, I think it depends. There are multiple authors, and apparently some authors are better than others. So I think I started down here. All right.
Yes, you have videos for 8.1 and 8.2, but not 8.4.
Yeah, all right. Okay. All right, well, so here's the first question. And this question is motivated by the formula for determinant, which is a sum over permutations. Right? The theoretical, the defining formula for determinant is a sum over permutations of a product of terms. And he does mention that that product of terms includes one from each row and one from each column. So can I get back there? Yeah, here we go. So here's the basic expression here that you're looking at a product. If it's an n by n matrix, you have a product of n terms. The upper index is the row index, lower index is the column index, and the column indices are a permutation of the row indices. So the numbers 1 through n all appear in the row index, and they also all appear in the column index, but they're scrambled. So for instance, in a 3 by 3 matrix, you would have terms, let me see if I can have a 3 by 3 matrix here, if I can find one. Well, I can just use this one. Imagine this was a 3 by 3 matrix. You'd have one term that has this one, first row, first column, second row, second column, third column, fourth row, fourth column, but you could also have first row, first column, and then third row, second column, second row, third column, fourth row, fourth column. As long as it's like there's a chess puzzle that talks about placement of knights, and you're basically trying to place one knight in each row and each column. You don't have two knights in any row or column. And, so if you look at the terms for the 3 by 3 case, you'll see that that's the case. Actually, I think maybe they have that here. If you look at the 3 by 3 formula. Well, so let me just leave it at that. That what you're trying to do in this exercise is to understand a little bit better how that summation works. So let me get back there. Okay, down to 7.3. Whoops, should be 8.3, sorry. Okay, here we go. All right. So let's see. So what we're asking in this problem, I just want to make sure you understand what this is talking about. So let's just read through slowly. Given any permutation sigma, and so sigma is a rearrangement of the uh, integers. Let sigma hat 1, 2 denote the permutation obtained from sigma by transposing the first two outputs. Okay, so basically exchange the 1 and the 2. So remember that sigma is a function. Sigma is a function acting on the integers, scrambling the integers. But the scrambling that's accomplished by this sigma hat 1, 2 differs from the scrambling of sigma. Basically, whatever sigma of 2 is, becomes what sigma hat 1, 2 of 1 is. And whatever sigma of 1 is, sigma hat 1, 2 of 2 becomes. So let's give an example just to see what's going on. Right. So, you can just define sigma as a, using the tableau form. Right, if I define a tableau like this, well, here's my tableau for sigma. Let's just look at one that goes from, that takes, that acts on 4 elements. And let's just choose one. I have to have 1, 2, 3, 4 in some order here, so that might be 2, 4, 3, 1. Okay. Then sigma hat 1, 2 would just be equal to basically the same thing, except remember that sigma hat 1, 2 of 1 is equal to sigma of 2, and sigma hat of 1, 2 of 2 is equal to sigma of 1. All right? So if I take a 1, 2, 3, 4, sigma hat 1, 2 of 1 would be sigma of 2. Sigma of 2 is 4. So I'd have a 4 here. Sigma hat of 1, 2 of 2 is sigma of 1. So I have a 2 here in the second row here. So this would be 2. Okay. So basically I don't know why it's making all that junk there. But basically you're switching these two entries in the tableau. All right. And it turns out that you can write sigma 1, 2 hat is equal to, I think it says this in the problem, T1, 2 composed sigma, where T1, 2 is the transposition of 1 and 2. All right. So again, sigma is a rearrangement, and sigma 1, 2 hat is a further rearrangement of the rearrangement. All right. All right. So. All right, so we have sigma hat, and then he says let f be this function from 1, 2, 3 to r. F of n equals n squared. All right, so f of 1 would be 1, f of 2 would be 4, f of 3 is 9. Okay. Here it says write out explicitly the following two sums. Note each sum will have 6 terms. Okay. All right, so let's take a look at this sum here. F sum over sigma. So let me copy this and see if we can get some handle on what this means. Scroll down, and we'll copy it.
Are you going to actually move this over to our notebook?
Yeah, I'll move it later, sure.
Okay.
All right, so let's do this. All right, someone just messaged me. I don't know who that would be. Let's see who that is. Who is messaging me? Okay. All right, so somebody's connection's not too good. All right, well, okay. All right, so we have this. All right, so let's see if we can do this. Remember that. All right. So we have 6 permutations, right? So we'll get 6 terms. Okay. Okay. And let's just write down the 6 permutations, right? What? How would you write down the first permutation? What can we remember? You can specify permutation by a tableau. It's basically a function from 1, 2, 3 to 1, 2, 3. So what should I put in the second row here?
149.
No, because it's a function from 1, 2, 3 to 1, 2, 3. I'm talking about sigma, not f. So this is the first sigma, not the f.
So just 1, 2, 3.
1, 2, 3 would work. Okay. All right. What would be this next? What would be another one? All right. You got whoever that's an awful whoever that is has an awful lot of background noise. All right. I heard Adam say 3, 2, 1. That works. That's another one. Okay. What's another one? I don't know who that was with the background noise. Was that Adam?
It's me. I'm in a hotel. It's Aaron.
Okay. All right. Well, I'm in a hotel too, but mine is a lot more quiet, I guess. All right. So what's in 1, 3, 2? That will work. Okay. So we've got 3 so far, but you could have to have 6.
2 to the first is
Right.
2,
Okay.
3, 1.
Okay. Where's my? Okay. Okay. I can do 1, 2, 3. And then I can do 2, 3, 1. That looks different. And then so that's 4. Then 1, 2, 3, 2, 1, 3. Okay.
Missing. 3, 1, 2.
Okay. 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 All right. All right. So let's see. Now, if I take this term, what is f of sigma of 3?
In the first one, it's 3, right?
Well, sigma of 3 is 3. What is f of sigma of 3?
I mean, as it's defined in the problem.
Yes.
Is that 9 then?
That's correct. Okay. All right. So yeah, we have fx equals x squared. All right. So that's 9. So let's look at the next one. What is f of sigma of 3 in this case?
It's 1.
It's going to be f of 1 is equal to 1. Okay. So continue, right? And then you're going to add, because it's a sum, you're going to add them up. Okay? So that's how you would evaluate the term on the left-hand side over here. That's how you'd evaluate the left-hand side. Right-hand side would be similar. Okay? You can write down these 6 permutations, whatever they are, and take f of that. All right, so that's basically, I just want to make sure you understood what these summations mean. because that's certainly basic to this problem. All right. So you can write down those two sums and see if you can see some relation between them. Now this was the case where we had sigma 1, 2 was you transposed the 1 and the 2. Part B is generalizing that to transposing any two of these. For instance, sigma hat jk transposes the j and the k. You could have sigma hat 2, 3, sigma hat 1, 3. I guess all you can have is 1, 2, 1, 3, and 2, 3. Those are the only three you can have. And it turns out, whoops, that G should not be there. Sorry, that G is a mistake. So you can note that on your own paper that this G is not supposed to be there. It's just F. And I guess I'll have to put in the correction. So basically this problem is to see why it works in this simple case, and then you have to say why it's going to work in this more general case, and then see if you can generalize that to the set from, instead of 1, 2, 3, the set from 1 to n, and state why the equalities are still true. And then you go one step further. So here, in fact, this is what I mentioned, is that this sigma hat is basically the original sigma composed on the right with the transposition. Right? So a transposition is a permutation. So in this problem, what you want to show is that these two sums are equal no matter what permutation you put in here. And the idea is that, I think there's a hint there too. Let me see if I can see if my mouse is going to work here. And then I give you a hint there that any permutation can be written as a product of transposition. So basically you want to build up this statement about general permutations from the statement that you made about individual permutations. And then there's another misprint there. That should be K sub L. So I'll have to fix that misprint too. That's a subscript on the K. Okay? All right. Any questions on that one? All right, just follow it through step by step and see if you can get the answer. All right, I think I skipped 7, I believe. Yes, I skipped 7. We'll go on to 8. Okay, now, all right, now problem 8 says, let M prime be the matrix obtained from M. I don't want this. I don't know why it's there. By swapping two columns I and J. Show that determinant of M prime equals minus determinant of M. All right, now, this, if you've watched the video, read the chapter, this should be a little bit familiar because in the chapter it talks about swapping two rows. And there's a proof in the chapter that if you swap two rows, you switch the sign of the determinant. All right. Now here I give you a hint how you can prove the same thing for columns. It says use this statement illustrated in figure 8.6 and recall what happens when a matrix is multiplied by the elementary matrix Eij on the right. If you don't remember what Eij is, go back and see. It's basically the identity matrix with the I and JJ, well, the ith row jth column and the jth row I column basically switched. I'm sorry, the ith column and the jth column, the ith row and the jth row of the identity matrix are switched. So you can see a picture of that in the chapter. And I think we have actually done a problem talking about what happens when you multiply matrix M on the right by this kind of elementary matrix. All right, so I think with a hint that's not going to be too difficult. So any questions on that? I think the hint will be helpful. Let's go on to 9. 9 says, suppose that row M of a square matrix big M is a linear combination of two other rows. So you know what linear combination is. That means that if J was 3 and K was 4 and M was 5, that means the fifth row would be some sum of the other two rows. And this is annoying. I don't know why it's doing that. And I don't know why it won't close it. It's going kind of nuts here. It's not paying any attention to me. Well, we'll just let it be spastic. All right, so I don't know what's going on here. Let me pause my video. All right, so what you're saying is that one row is a linear combination of two others, and then it says write M as a product of elementary matrices times a matrix that has a zero row. In other words, you can take a matrix that has a zero row and use elementary row operations and come up with this square matrix big M. All right, that's the idea, that you can take a matrix with there is a matrix with a zero row, and you can apply elementary row operations to that matrix and come up with this matrix M. All right, so it's up to you to figure out how to do that. And in the chapter it talks about how if you have a matrix with a zero row, the determinant is 0. And the reason for that is in that sum of terms that we talked about with the different permutations. It's a sum of products of terms, and every one of those products has a term from every single row. So if one row has all zeros, then every single one of those terms in that sum of permutations is going to have a 0 factor. All right. So once you can write this M as a linear combination this M is a product of elementary matrices times a matrix with a 0 row, you should show why that implies that the determinant of M is 0. And then do the same thing with columns. The difference between row and column basically is that for row you apply the elementary matrix on the left, and for column you apply the elementary matrix on the right. Okay, so let me go down to the next one. So you're getting a lot of practice with elementary matrices here. Our next one, let E be an elementary matrix. Show that the determinant of E is equal to the determinant of E transpose. Okay. Now there's 3 types of elementary matrices, and you can just go through and try it for each type. Some of them are rather easy. For instance, there's one type of elementary matrix where you multiply corresponding to multiplying a row by a constant. Now, if you look back and see what that elementary matrix looks like, it's a diagonal matrix. If you have a diagonal matrix, then the matrix is symmetric. So in fact, E equals E transpose. So in that particular case, it's rather straightforward to prove that the determinant of that type of elementary matrix is equal to the determinant of its transpose. And the others are not so difficult either. All right, so I'm proving that first for elementary matrices. I'm not trying to show this for general matrices, just for elementary matrices. Okay, and like I said, you'll have to do that in 3 separate parts. All right. All right, then part B says any non-singular matrix can be written as a product of elementary matrices. Use this fact in part A to show that the determinant of M is equal to the determinant of M transpose. Now, you will also have to use this fact up here. This fact in figure 8.6, this fact is actually saying that the determinant of the product is a product of determinants. All right. So first, the strategy is you show that M is written as a product of elementary matrices. Then you use the fact that the determinant of the product is equal to the product of the determinants. And you can use that to show that the determinant of M is equal to the determinant of M transpose. So you're actually going to have to express both M and M transpose as a product of elementary matrices. And then show that those two products have the same determinant. All right, problem 11 is similar to problem 10. Problem 11 says you're doing basically the same thing. Instead of with transpose, you're doing it with inverse. So you're going to look at the three types of elementary matrix and show that their inverses are also elementary matrices. And then find the determinants of those inverses. That's in part B. And then you're going to use that information to find a relationship between the determinant of a matrix and the determinant of its inverse. So problem 11 is very parallel to problem 10. Problem 12, you start out with a 2 by 2 matrix, A. So you can write A as A, B, C, D. Then you can look at A plus T times I2. So A plus T times I2 would be, so if A is equal to A, B, C, D, then A plus T times I2 is equal to A plus T, B, C, D plus T. Sorry for all the chicken tracks there. And then you can find the determinant of A plus TI2. Okay? Just use the regular determinant formula on this 2 by 2 matrix. And what you'll get is a polynomial in T. And then what you're supposed to do in the problem is figure out how do you express the, here we go. How do you express the coefficients of that polynomial in terms of the determinant and the trace of A? If you remember what the trace of A is, it's the sum of diagonal entries. So this is for 2 by 2, and then part B you do 3 by 3. And part C, make a general statement from that 2 by 2 and 3 by 3 case, see if you can see the pattern and make a general statement and prove it. And the part C talks about trace, and part D talks about determinant. You find when you do A and B that trace plays a particular role, and then you also find that determinant plays a particular role, and then in parts C and D you want to look at those separately. Let me pause my video. All right, and I think that's the end for section 7.3. And then I have a couple of problems here. Section 2, 3, 4, 5 in section 8.5. Let's look at those. Okay. Sorry.